Welcome again to 858. Just one small administrative point before we get started. Because the class size continues to grow, I've been in contact with our department administrators who are thinking about devoting a TA to this course, a marker to the course. But we need to break a 10-person limit. So if you have friends you want to encourage to take the course, or if you haven't registered yet and you're thinking about registering, sooner is better, because that may allow us to get a marker which actually could further enrich the material that we cover as far as sort of assignments and allow additional resources to be put into helping to contribute to projects and that sort of stuff. So if you're not registered yet and you think you'd like to, please do so soon. That will let us get that in place. So that's administrative matters. So for today, what we're going to be doing is we're going to be talking some about the video I asked you to watch, and using the Blackboard for the first part of the lecture, the whiteboard, and then we're going to be taking a glimpse at two pieces of software we're going to be using this term. A piece of software called Vensim, which is very decidedly for system dynamics modeling, and then a package called AnyLogic, which can be used for agent-based modeling, but also system dynamics and also discrete event modeling. Okay, we're going to be seeing in hybrid models, which weave all together. So we're going to take a glimpse of both of those in an interactive way. And you recall that we're aiming here at an experience where we take advantage of our time together for interaction. So we're going to be using these sessions for a lot of discussion, questions, back and forth. And I'd like to encourage anyone to speak up with questions at any point and to contribute to this discussion. Okay. So I asked you to watch a video. In the video, talk broadly about motivations for modeling, so the context for modeling. So that was a video from my 394 undergraduate course. So I'd like to talk about some of the points in that video and some points that weren't in the video. Okay. So the video talked about some ways in which we use dynamic models. So what do I mean by a dynamic model? So what other sorts of models are there? If I talk about models, I say I'm a modeler. I said, this is a really impressive model. What do I mean? What could I mean? What sort of models are there? What do they have in common? Computer models in particular. So when we say that I have a model of some situation, what do I mean by it? Model of some processes, a model of a physical system. Sorry? Okay, some mathematical elements. So that's often tied up with it, but I could draw a model, and we'll see models in the system dynamics portion of this. And in fact, we'll see glimpses of them related to agent-based models, which are what I call semi-qualitative models, or if you want to flip it around, semi-quantitative models. So we might talk about, for example, we might talk about a cycle of addiction, in individuals where you have, substance abuse, level of substance abuse, and that, level of substance abuse, the higher that is, the more that contributes to something like, inability to focus, and that leads to, if they have or we can make it ability to focus. There's an art with this, and naming it in a positive direction. It lowers their ability to focus relative to what it would have otherwise been. And having an ability to focus helps on, holding a job, something like that. Ability to hold a job, it gives a sense of self-efficacy, what they can do in life, and that sense of self-efficacy affects substance abuse. Holding a job increases a sense of self-efficacy. Increasing a sense of self-efficacy lowers the chance of substance abuse. And I could assign this sort of a model. I could say actually it's a positive feedback loop, so it's a cycle. It's a cycle, a reinforcing feedback. So it gets worse and worse and worse. Someone who's on a downward spiral here uses, abuses substances more. They have an inability to hold a job, low sense of self-efficacy, and they turn to substance abuse to deal with the pain and frustration in part. And we could add extra features in this having to do with dissolution of relationships and a whole bunch of other features. Is that a model? In what sense is that a model? Is there math directly here? No, although we have these polarities which will be turned out to relate to partial derivatives of all things. So the ways in which a change in this leads to a change in that, all other things being equal. Why is this a model? What is it that makes it a model? Why is it that we can speak of it as a model? Okay, it's an abstraction from reality. It hides a lot of details, but it tries to capture certain essential features of the situation. It's a simplified version, you could say, crudely speaking, of some phenomena that we hypothesize to be the case. We might hypothesize, we might have a lot of evidence for this, in particular situations, but we might build models where we don't have a lot of evidence, where we're building models to sort of characterize our guesses for how things are operating. So a model is a simplification. It's kind of a mimic of aspects of reality, but it inevitably involves abstraction. And for those from a computer science background, you could argue that computer science, one of its distinguishing features is its focus on abstraction. Taking a very complex situation and capturing certain features of it in a way that allows you to solve problems. In some ways, when we build software, it's exercises in abstraction. We build up tools that are general enough to be used under a wide variety of circumstances, for example. And in modeling, we're taking abstraction. We're taking something that's extremely complicated out in the world and creating a simplified version of that. Why? Why do we do that? What benefits come from doing that? Why create a simplified version of the world? Isn't that wrong? Is this wrong? Well, it captures certain. Does it capture everything about the situation? Everything that affects self-efficacy, everything that affects their ability to hold a job? No, it doesn't capture everything, but it captures some features. And I argued that an analogy is like a map. It's like a map. You have a map of Saskatoon that's a driving map. Is that a perfect representation of Saskatoon? Is that does it show everything about Saskatoon? No, not everything. It shows many of the essential details, and it helps for what the purpose, a particular purpose, which may be driving through Saskatoon. So it shows you how to get from A to B in Saskatoon in a car, right? Does it show you something about where electricity would fail if lightning hit a certain substation? No. For that, we'd have a map of a different sort. We'd have an electrical connectivity map, right? Does it show you where flooding is going to occur if we get a heavy rain? No. For that, we'd use a hydrological map, sort of with topography shown in it, so where the water would flow to, what's elevated, what's not. Maps are simplifications too. They're models. They hide certain detail, they reveal others. And the models are, ladies and gentlemen, typically specific to purpose. So a driving map is not going to be of that much use if you're trying to identify the cause of a brownout in Saskatoon, the cause of an electrical failure. It's not going to be that useful if we want to figure out why certain areas are flooding and not others, because it doesn't show where the drains are and that sort of stuff. If we wanted to do that, we could use a different sort of map, right? Is a map wrong because it doesn't show those details? Not really. It may be fit for use for certain things and not for others. But we have to bear in mind sort of what its use is, what its intended purpose is, the purpose for which it will be used. So within this class, we're going to be talking about models. Models, which are simplified versions of hypothesized reality, hypothesis aspects of reality. They're in a way, they're theories. They capture a theory. They capture a theory about how things are, how things work out there. Now, we're going to be talking in this class specifically about a type of model called a simulation model. Simulation model. What do I mean by, so just like model has many terms, I have friends so I worked for a little bit of time in Southern California. In Southern California, worked on applying models to policy issues in Southern California. Southern California is a strange area. It's distinguished by many things, but one of them is it's got a very sort of fashion-conscious culture, etc. And so one of my students complained that I had corrupted her because I had started her using the word model to mean like computer model rather than like a model on a catwalk walking back and forth. And you know, one of her friends said, "Oh, let's go to a modeling show." And she was wondering what sort of simulation models are they going to have here. And actually, they meant like a fashion show. And I guess their friend was a bit disappointed that they didn't understand that. Anyway, so models mean all sorts of different things. And here, we're going to be talking about a specific class of model called a simulation model. And we're going to be talking about system dynamics modeling as one of the main sorts of simulation model. We're going to be talking about agent-based modeling. So major one we'll get a sort of little glimpse of. In Southern California, they might call it a cameo appearance of a discrete event modeling, or process-centric modeling. So we're talking about a simulation model. What do I mean by simulation in this context? Well, this is a subclass of what I'll call a dynamic model. Dynamic models. When we think dynamic, I'm going to use that term a lot in this fun. Dynamic model. This is a dynamic model. What do I mean by that? We actually use that term in computer science too for other things. We talk about, you know, this types being dynamically realized in this language, or that we're going to make use of a dynamic approach to classifying things. What do I mean by dynamic? Yeah, changes over time. Time is the central component of this. In engineering, we talk about statics and dynamics, and dynamics have to do with the time behavior. So here, we're talking about dynamic models, models which are capturing things over time. I'm sorry, I just wanted to link these together. I'll put it up here. It's better if I say dynamic model, okay? So, abstractions of reality that capture behavior over time. How a system behaves over time. You could think of it as theories about how it works that describe how it will behave over time. So we build a model of a bridge to help us understand how it behaves over time as wind blows on it, so we don't get galloping Gertie. Does anyone know galloping Gertie? Good. It's Tacoma Narrows Bridge. And there's actually videos of it. You can go see it. I used to show it in another version of this class. and you can see it oscillating, exhibiting its normal modes, and at some point the oscillations became too much and it ripped apart, and it collapsed. It was a disaster. No one was killed, no one was hurt, but it was a loss of hundreds of millions of dollars, or the equivalent of hundreds of millions today. So dynamic models. We build dynamic models to understand behavior over time. Okay, and dynamic models explicitly give us some information about how things change over time. Are all models that say are mathematical, are they dynamic? Give me an example of a mathematical model that's not dynamic. Doesn't include behavior over time. Anyone? How many people here have taken statistics before? Statistics course. Okay, most people. So how many people have seen regression before? You regress one variable against another. So we could regress server, server throughput against number of users and diversity of requests or something like that. And say, oh, there's a function between those and how the server behaves for CS related things. I could regress mosquito populations against rainfall and so the mosquito population as a function of some function of, and maybe I'll just write it this way. I'm not sure I'm going to propose this. Some beta, some constant plus, some second beta times, the amount of rainfall measured in millimeters, plus some beta 2 times the temperature or something like that. And this is mosquito pop. Okay. I could write down an equation like that. Yeah. Right? Predictive equation. First of all, is this a statistical or mathematical model? What do you call that one? Yeah, it's a model. It's a model. It captures some association between, on the one hand, mosquito populations and the other things. Is this a dynamic model? Okay, fair enough. What if they're not? No. It doesn't tell us about how the mosquito population will change over time. So we have rainfall right now. It's just finished raining. Do you think the mosquito population will be giant because it's rained a lot? Probably not. There's some time delays associated. And this model abstracts away from that. Just sort of says if recent rainfall has been high, the mosquito population tends to be high, but it abstracts how soon it takes temperature to affect the breeding cycle of the mosquito, lead to actual mosquitoes in the water, the pupae and larvae that are lots of numbers, and then how quickly they come out and bite us. Right? It abstracts away from that. It abstracts away from how quickly the rainfall has an effect. It just allows us to sort of generally say, okay, there's this statistical relationship with this association between. It's not by in itself a dynamic model. We might similarly regress, crime and poverty and education levels, etc. And create models there, but they're not dynamic. They're not characterizing things over time. So dynamic model has this extra element of time, capturing behavior of the system over time. Why might that be important in some cases? Why would we care about behavior over time? Let's take this case, mosquito population. Why do we have to care about behavior over time? Good. Yeah, delays are really important. So it could be a delay between a change and an effect. What's another reason we might care about behavior over time? Okay. Okay, so for certain periods it may not be correct, so like if we have a huge rainfall that just ended, it'll be off, and so maybe we want to take into account these delays, for example. That would be an important thing. That'll be an important consideration. So that's good. How if we want to capture the fact, unfortunately, this is not a great example, but here, let's take this one where we have this little model up front. Could we regress substance abuse based on whether or not people hold a job and their ability to focus? Could we create a little regression equation among them that describes their association? Yeah, we could. We could, holding a job as a dichotomous variable, yes and no, or the number of hours they work per week and their likelihood of substance abuse, maybe go down something like that. Now that doesn't tell us, so there's maybe some relationship there. It doesn't tell us how quickly things would change if we got them a job, right? If we were to help them get a job. It wouldn't tell us so there's a delay there. And it wouldn't even necessarily tell us, the statistical relationship won't even tell us causality. It tells us an association. This is associated with that. It's correlated with that. But it's not telling us how if we change one thing, it would change the other. How quickly, how much, and over time, how it would change. Maybe at first it would change in an adverse direction, better, or what have you. So dynamics can often help us reason about behavior over time in a way that helps us understand what to expect, how soon, and particularly from changes, okay? So dynamic models often are causal in nature. We try to characterize how the system works. And so I'm going to put up here as a subset of dynamic models, there's sort of causally oriented dynamic models. So sort of causal dynamic models, and these try to characterize what depends on what, so that we can reason about counterfactuals. So we could say, if this were different, how would it be different? How would the observed patterns be different? How would the results be different? And that goes more than we do with statistics. With statistical relationship, we capture some aspects of the situation, but often we're not capturing certain key aspects, how it will be different in the relationships if something were to change. Dynamic models were explicitly doing that. We try to capture causal structure, a hypothesis about, completely certain about, we try to capture what we, our best guess in ways that might allow us to reason about it, etc. Now a simulation model is a particular type of dynamic model. Not all dynamic models are actually simulation models. Give me an example. Can anyone give me an example of a dynamic model that describes things over time that's not a simulation? It has nothing to do with a computer simulation, I'll put it that way. Good, yeah. I could give some, mosquito population as a function of T or something like that. That's giving something that's dynamics, it's a function of T, right? And maybe I'm going to say it rises, some beta plus e to the alpha t or something like that. So it rises, something like that, right? Could that a dynamic model? Yeah, it's a dynamic model. It's describing things as a function of time, and that will get us a certain point. How many people in here have taken a course before or seen differential equations? Okay, so some people recognize you can write a differential equation model, right? I could write, so dx dt, equals alpha x minus beta y, and I could write dy dt equals, gamma x plus delta y or something like that, right? I could write that, and I can actually solve that. For those who haven't taken differential equations course, I could solve that. I could compute its eigenvalues, and I could I could decompose this in a nice way, and I could describe it as a sum of complex exponentials. So it's going to be, you know, it's going to be some, you know, constant, and I'm using so many constants up here, I'm going to have to be careful. It's going to be some, you know, e to the a times e to the bt plus c times e to the dt, something like that, where these could be complex constants. So I could write that, I could solve it. Do I have to use a computer simulation for this? No, I could actually solve it. I could write down what its solution is. But ladies and gentlemen, in certain cases we can't do that. This gets too hairy, especially because of the presence of a certain thing called nonlinearity. The reason I can solve this is because I can take it apart in a certain way. Take it apart into pieces that can be described in what's called the linear fashion. And you can do that for a certain subclass of equations in a very nice way. And particularly with linear algebra, you can do it in a very nice fashion. And if you have some vector dx dt equals some a to the alpha x, and this is a matrix, the solution is going to be something like e to the at, and this is a matrix here, and it's a sum of matrix exponentials, and it's all, it's just chocolatey goodness. But if you really understand it, it's beautiful, but it's extremely limited. We can only do this for a small subclass of problems. And we can always linearize and say, well, around this certain point, it's basically linear, but there's great limits to what we can do. So if we want to have even differential equations that are nonlinear, and we want to be able to simulate them, we want to be able to solve them over time, we often have to do so numerically. We don't have the option of just writing down a solution, of finding what's called a closed form solution, meaning a solution we can write down as a formula. Instead, ladies and gentlemen, what we need to do is we need to program this into a computer, and we'll see some languages doing that, some which you don't even think you're programming. We need to put this into a computer, and we need to say, go solve it. And in its most naive form, it will go forward, step by step, little dt's, little delta t's, stepping forward and simulating what x and y are over time. So one of the big characteristics of a simulation model, ladies and gentlemen, one of the hallmarks of it, is we're simulating the evolution of a system state over time. What's going on at the system at a given point. We're simulating how that changes over time. How many people have diabetes at this time? How many people have end-stage renal disease? How many people are normal glycemic, have normal blood sugar levels? And seeing how that changes over time. Or maybe it's a mosquito population. Simulate how many mosquitoes there are, how many how many birds that are being bitten by the mosquitoes, and how many humans are being bitten by the mosquitoes. We can simulate that over time. We simulate the evolution of a state over time. So evolution of state over time. Okay? So these are in simulation models. We run them on a computer because we don't have any other option. There is no known way, once these equations get complex enough, to solve them in general. And I could easily make this equation such that we can't solve it in general. First of all, I could put in some nasty terms here on the right-hand side, which would be nasty. I could start by putting it gets quite a bit more complex if you put in cross terms here. So if it's multiplications of x and y. Now we have this multiplication, and the behavior becomes much more interesting. Or I could put in, y times sine of x or something like that. And basically, very easily I can make that intractable to be analyzed in closed form, and I need a simulation model. So what we're saying is, folks, if we want to understand big picture, I don't expect you to understand all this stuff, but I do want you to understand one important feature of this, which is if we're trying to understand behavior over time of a system, it doesn't require much complexity of that system for it to require simulation. Okay? We just don't know how to do it by the state of the art to just write down the answer by looking at it. We can do it for very, very simple systems. But beyond that, we need to turn to the computer to simulate. So step by step by step, in the most naive form, to go through and solve this thing in a way that simulates the evolution of the state of the system. What is happening at this point, at that point, at that point, simulating it step by step in a way that helps us understand how that system behaves. Okay? That is a characteristic of dynamic models that we're going to be seeing all through this course. We're going to be seeing a lot of different types of models, but they all share those in common. Some will be called system dynamics models. We'll be seeing that today. Some will be called agent-based models. We'll be seeing that also today. Some will be called discrete event models, sort of process-centric. All of them involve the simulation of system state over time. And some of them would just bring a mathematician to their knees. Maybe make them cry. Because of the complexity. We don't have the tools mathematically to solve these things, anywhere close to it. And actually, sometimes it makes me feel kind of bad, because I'd love to get some of the mathematical insights like that from simpler models. And for some subsets of these models we can, but for really complex agent-based models, we don't have the tools to do it. For some of the system dynamics models, we're going to be able to see, actually, how we can understand behavior over time in a general way. A way that's not just with some particular assumptions, but it tells us something about how the system can behave in all possible configurations. We'll see how we can do that. But and for many agent-based models, the only thing we can do is just run it with some particular assumptions and see what results. Run it, see what results. We can't calculate a general answer. So ladies and gentlemen, that was sort of a little bit on types of models and that sort of stuff. And I'm going to nuggetize that. Kurt, remind me to keep on nugget. Okay. So this is like